Is there anyone from the organizer side? Means should we wait for 1-2 minutes? Then some more people are expected to join, or we can start?
So we can wait for 1 or 2 minutes because the numbers are people are joining in. So
okay. So let's wait for 2 minutes.
Sure. Maybe in the meantime, I can ask you how are things going there? Did everyone, like, do people go for lunch together? And
oh, this is in distributed mode, so
for you as well. Okay, but the students are together, right? Like
some of them.
Some of them. Okay.
Yes. This is kind of hybrid mode conference. So
yeah.
excuse me, I think we can start. It's already 3.
Yes, it's important to be on time, and we have to other things also. So I would like to welcome everyone who has joined this session, and also the speaker, Nitica Sakharwade, and it's my pleasure to introduce her. So she did her master's from IIT Kanpur, and subsequently she did her PhD with Professor Lucian Hardy from University of Waterloo on an operational road towards understanding causal indefiniteness with post-quantum theories. And causality is perhaps the most fundamental rule which governs everything, means apart from minimum energy configuration, everything obeys causality. And so her research interest in that sense is foundational quantum mechanics or quantum foundation, and of course the related aspects of quantum information and communication. And at present she is a postdoctoral fellow in International Center for Theory of Quantum Technologies at University of Gdansk, Poland. And today she will talk about her works with many aspects of applications of causality will appear in that, but the specific title of her talk is how models of indefinite causality can be understood within the Causaloid Framework. So I'll not take more time. I'll request Nitica to share her slides and start the talk.
Thank you so much for the lovely introduction. Let me just make sure that the share screen is working. So let me know if you can see the screen.
Okay, it's coming. Now it's visible.
Now it's good? Okay. So, yeah. So, okay. The only thing is, if you can give me a warning of maybe when 15 minutes are remaining, that would be really nice.
Sure.
And I mean, we have a slot for 1 hour, but I would like to, like, if anyone has questions, please feel free to ask, maybe put them in the chat or and ask questions. And I would like to keep some time in the end as well, if people want to have a short discussion. Okay. Great. So I think I was going to tell a little bit about myself, but that was already done really well. So yes, I did my master's long ago in IIT Kanpur, and it was really nice to see some speakers at QIQT, like Anand sir and Vandre sir, also speaking at this remote conference. And now I'm going to talk about mostly works based on my PhD thesis, specifically chapters 4 to 6, and also ongoing work that is offshooted from this. And okay, so essentially, I want to talk to you about what the Causaloid framework is. And to motivate it, we'll talk about indefinite causality and what that means. But you have seen some talks about this in this QIQT workshop already previously. Fabio Costa gave a talk this week. So you saw the process matrices. So these things are in the same area of physics. And let me motivate what we even mean by indefinite causality. So there is a paper by Lucien Hardy back in the early 2000s. It's called, as you can see, the title is Probability Theories with Dynamic Causal Structures, a New Framework for Quantum Gravity. And really, the essence of what he was trying to say in this paper, the motivation was really trying to understand the radical aspects of general relativity. So general relativity is in a way deterministic, but it has dynamic causal structure, and you need to define, let's say, the state on a hyper-Cauchy surface to figure out what happens before and after, to define the causal relations between different events. On the other hand, in quantum theory, we have a fixed causal structure. If you look at quantum circuits, there's some state, and irrespective of what the state is, the order of events that are in its future, like the gates that will be applied, cannot be controlled by the state. So there's a notion of a fixed causal structure, which means that the order of events are fixed. But on the other hand, in quantum theory, the radical aspect we want to focus on is its probabilistic nature. And really, if we want to go towards some framework of quantum gravity, it would require necessarily to marry these radical aspects of both these theories, dynamic causal structures and probabilisticness. And one could actually go further and think that the probabilisticness can actually make the causal structure itself indefinite. And that is what we really mean by indefinite causal structure. And then following this paper, so this is the paper where the Causaloid framework was introduced. And following this, there has been a lot of research in this field, including the process matrices, as well as quantum combs, and more frameworks. There's just a vast literature out there. But most of them focus on the beginning of the literature focuses on trying to study this from a post-quantum lens, which means that you have Hilbert spaces, and you can think of quantum combs as these supermaps over CPTP channels. So something that takes a channel and gives you a new channel back. And therefore, you have to assume that the wires correspond to quantum systems. But on the other hand, there is a different literature which pertains to the reconstruction of quantum theory, and also in the early 2000s, which was kickstarted by this paper, Reasonable 5 Axioms for Quantum Theory. And what is done there is that you want to talk about a landscape of theories, logically possible theories within which quantum theory lies, by identifying some principles. And given these principles, um, you want to identify what principles govern quantum theory without assuming necessarily Hilbert space structure and so on. And the approach in the Causaloid framework is similar, but it goes beyond GPTs. So this landscape can be called the generalized probability theories. So you only assume some preparation transformations and measurements, and you assume that you get probabilities back that are real and positive and between 0 and 1. So now here you can think of the Causaloid framework as a landscape of theories which have GPTs that also allow for indefinite causal structure. And now we can discuss how it was actually formulated. So part of my thesis was finding diagrammatics for the Causaloid framework, so a diagrammatic language to understand it. And I'll be using these diagrammatics in this talk. The next thing we did was we tried to, so once you have a landscape of theories, you want to categorize them and understand them in some manner. And we do it with respect to a hierarchy we introduce, which I'll talk about. So I'm just giving a short outline. And then finally, at the end of the day, we want to understand where things we already know fall within this framework. So I will give you two concrete examples. And when I say concrete, it's still quite abstract, but the set of DO tensors. So a DO tensor is a framework which are a class of generalized probability theories, which have some rules like local tomography obeyed. And we show that these fall within this hierarchy in a certain way. We also, so this is on the side of GPTs. From the other side, we show how the process matrices, an example of indefinite causal structure, fall within the Causaloid framework. And then I will end with some open questions. So now I will spend some time trying to explain what the Causaloid framework is. So the story goes as such. You can imagine a person in a box, and without loss of generality, it can be Lucian. And now this person really, what they have is they are inside this box. They do not have access to anything outside in the world, but they want to understand the underlying theories in this world. And the way they do it is by they get a stack of data, and they have this data which is in the form of cards, and each card contains some information. So what is the information contained on this card? It has some location, some actions. You can think of it as the settings of an experiment, and some observations. So given some settings, what happens, right? So you can think of it, you can think of it in many ways, but a location can be something relational, saying that I am next to this person, and this person is next to someone. It could also be much more concrete, like GPS coordinates, right? And actions and observations can also depend on what you have. And now really you can think of these actions providing you procedures and these observations giving you outcomes. And now this person is given with this stack of cards with all logically possible events happening in the world that can happen in the world are in these cards. And they need to organize this. They need to reduce this set of cards to the minimum possible to still be able to predict the probabilities for events happening in the world. This is the goal. And how do they do that? So they start by organizing the cards first into, if some set of cards have the same location, they'll make it into one stack. And you can think of that as a set. So you can think of it as a set, an elementary region. We use the word elementary if you cannot fine grain further this location. So you cannot further figure out. So a non-elementary region would be where you say anything within this room is considered a region, but an elementary region would be literally just every entry of this particular location being in a stack. Good. And then you can find subsets of given a region, you can find subsets that have some procedure F. So this is literally having some procedure in this region, and these are sets. So you get a new set. And the third set you get is given some region procedure, what outcomes you see. And then of course you can deduce that YRI would be a subset of FRI, which would be a subset of RI. And now we're interested in these probabilities. So here, this Y is the outcome. So we are interested in the conditional probabilities of the outcome in some region, given the procedure in that region, of course, but also the outcomes and procedures anywhere else. And once we have this, we say that at least at an operational level, we are done. And then one can spend more time understanding the ontology of the theory, but that would be an undertaking for a later time. And really the story of this person in a box forces the person to employ this operational methodology. Good. So now we have this. So we now have this stack of cards, and one can go back to the stack of cards and calculate probabilities just in a frequentist method by just saying, what is the size of this procedure set versus the region, what is the size of this outcome set versus the region, and so on. Like one can do that. And therefore you have these probabilities. We'll start with these joint probabilities because one can always go back to conditional probabilities at a later stage. So now you can think of this as joint probabilities. What are these wires? So each of these wires correspond to a different elementary region, and the alphas correspond to indices for the number of the cards. So now the number of the cards can be really large. And the number of the cards can be really large, which means that alpha belongs to a really, so, okay, just to put this in perspective, you can think of a Stern-Gerlach experiment. So your procedure is, let's say, just the angle at which you're sending the system. And now, because these cards contain all logically possible settings, you would have, in principle, an infinite number of settings. So these alphas are really these labels. And now we can actually try to write this in a generalized bond rule as some inner product between a measurement and state. But notice that when we talk about states and measurements in ordinary quantum theory, we have a notion that the measurement comes after the state. And we already have this implicit notion of causality between them. So we have to go to a generalized notion of measurement and state. And the way you do it really is to say that the state is something the region cannot control. So it's basically something that's prepared by the rest of the regions. And the measurement is literally the procedures as well as the outcomes that you can do that give you these labels, these alphas. So now we are really interested in this measurement R over these multiple regions. And going forward, so yes, I missed one thing here. So now, as I said, these alphas are correspond to really big sets, indices in big sets, but the point is that any physical theory correlates this operational data. So if there's any correlations, any physical theory that's not completely arbitrary, then you will have these correlations, and you want to use these correlations to compress your sets, therefore your cards, and we call this physical compression. So this is not the compression you see in like channel compression or like encoding decoding schemes. This is the physical compression you get from considering many possibilities and the structure, the mathematical structure that underlies these correlations. So in the Causaloid framework, there are 3 levels of compression. The first 2 are provided here now, the tomographic and compositional. So you can think of tomographic compression literally on a single region such that you find a fiducial set that will be able, so you choose a fiducial set, you know what happens for these fiducial set events, and from this set you can do a convex combination over these entries to get any other probability for another setting. And therefore now you might go from some sets that were really big, these gammas, to omega sets. And now, because you do this tomographic compression on each region, you have a Cartesian product between the sets. So these labels L1, L2 belong to omega 1, omega 2, and so on. And therefore, this tuple belongs to this Cartesian product. And maybe a bit about the physicality of what tomographic compression means is this is something you already know, you already use. When we talk about a qubit, we don't write down the state with infinite entries, we do it with a few. We know we need only 4 real numbers to express a qubit if you do not assume normalization. But on the other hand, for a classical bit without normalization, you need 2. So actually, the tomographic compression also differentiates different theories like classical theory, quantum theory, and PR boxes, for example. And so this is things we kind of know already. And then one can ask, what is the next level? So now you already did tomographic compression on each region, but what if you had done tomographic compression on all these regions together? Would these be different? Of course. And this difference is captured in this compositional compression, which takes regional tomographically compressed entries, and basically it captures what are the causal correlations between these regions. So a priori, when you started with these regions, you had this data and you had no idea how these regions are causally related to each other. And if you have some non-trivial compositional compression, then you would know that there is some causal relation. So if you actually start with a system that are all spatially separated, then the compositional compression will be trivial. But on the other hand, if you have time-like separated events, but actually not just time-like separated, but more so causally adjacent, such that only regions that really are causally adjacent can influence each other's correlations completely. And that's captured here. And now we have this new indices K1 to Kn. And this belongs to this omega set 1 to n, which is a strict subset if you have non-trivial compression of this Cartesian product. Good. So now we have done 2 levels of compression. We are almost halfway through the talk. And now we can define the 2 major implications of the Causaloid framework. So now you can define what is the Causaloid. The Causaloid is this lambda, this bold lambda, and it's literally just a set of all these elementary region, the tomographic compression over elementary regions. So these lambda matrices. So these are represented by boxes, but these are basically taking, these are matrices that are rectangular, which go alpha times L. So they are rectangular, and they basically have they compress the information from all your observed data. Further, you can also list all the compositional compression over non-elementary regions, and just the set itself is the Causaloid. And the reason it's called the Causaloid is because if you are given this object, then in principle, you can calculate all probabilities for any event in all these regions. And therefore, you can calculate the conditional probabilities, which we were interested in. And therefore, at an operational level, the Causaloid prescribes the theory itself. And then you can have something called the Causaloid product. And the motivation for the Causaloid product is to have a causally neutral product. So in quantum theory, we have 2 kinds of product. We have sequential and parallel composition. So when we have parallel composition, we use the tensor product. If we have sequential composition, we multiply these matrices, right? So if we want to talk about indefinite causality, we need to necessarily be able to not make these demarcations unless required a priori. So the Causaloid product basically captures how regions are correlated with respect to each other. Either this can reduce to the tensor product, this can reduce to sequential composition, or something more general. And therefore, you only need in this framework a single product, and you don't have to define sequential and compositional products separately. Good. So now we talked about two levels of compression. There's one more left, which is called meta compression. And we will define meta compression and then define a hierarchy over it. So now I can basically write the causaloid again, but in a different form. So here what I'm saying is we have, we listed, so assume you have n regions and some finite number of n regions. Then you start with the tomographic compression here. And then you have compositional compression over 2 elementary regions, compositional compression over 3, and so on. And this is just rewriting what we had before, but in a more categorized way. And now you can define a hierarchy. And okay, so before we define the hierarchy, meta compression essentially would mean that there is some compression over the causaloid itself, meaning that you may not always require all these lambda matrices. So in physics, we have these concepts of isotropy or some transformation invariant physics, and really that should be captured. And we need not always need the compositional compression of everything. And therefore, what you can do is say that in principle, you can restrict the set given some rules of how to get back. So for example, if you can compress, if you want to do meta compression and remove these, then all you have to do is just have the set and a set of rules of how to get this lambda matrix back. And this is actually how we define this hierarchy. We cut it off. We cut off this the elements in the causaloid until D regions for some D less than N, where N is the total number of regions. And we define some rules such that you can get a lambda ON or lambda OD prime back, where D prime is more than D. And if you can find such rules, then you would say that in this hierarchy, this theory obeys and falls under lambda OD sufficiency. Okay. And now the rest of the talk really is trying to understand what this hierarchy means. Okay. So the first thing is you can have D equals to 1, which means that you cut off all compositional compression. You just cut it off here. But that would mean that once you're done with tomographic compression of elementary regions, you're done. And that would mean that in this physical theory, there are no causal connections at all. And this is something we are not interested in studying. So it's a trivial theory that we don't want to study because there's nothing interesting going on. There's no notion of causality. Then you can go to the next level, the next rung, and you can say we cut it off at lambda O2, and then any compositional lambda matrix of lambda O3, O4, and so on should be expressible as some function of lambda O1 and lambda O2s. And this is what we studied in detail, and we show that these two frameworks I was talking about, the DO tensors and the bipartite process matrices, actually fall into this rung. And now we will go through some details to substantiate this claim. Okay, so let's take a very simple example. Let's take n equals to 3. So this is the spherical cow version of what we're trying to do here. And then you can write down your causaloid. Just as you can enumerate all the lambda matrices. So you have tomographic compression between region 1, 2, 3. compositional compression between 1 and 2, 2 and 3, 1 and 3. So pairwise compositional compression, and then you have 3-region compositional compression. Okay. Now you can ask if you want lambda O2 sufficiency, which means that this lambda matrix should be expressible as some form of all the preceding ones. Then if lambda O2 sufficiency holds, then this diagrammatic equality can hold. And one can also write down the symbolic form. So, but for the sake of the talk, I'm trying to give you a more intuitive picture of how these things work. But again, feel free to ask questions. Good. So what's happening here? We have tomographic compression and we have lambda O3 applied here. And then we say if it's equal to tomographic compression and then pairwise compositional compression of 1, 2, 2, 3, and 1, 3. Notice that this wire is just passing through this. So this lambda matrix is still a pairwise lambda, a compositional compression matrix. Good. And if this holds, then now you can try to characterize these equations. So let's consider an even simpler case where region 1 and 2 are causally adjacent and 2 and 3 are causally adjacent, but 1 and 3 are not. So you can think of this in quantum theory as a circuit where you have gate 1, 2, 3, and then because 2 is in the middle of 1 and 3, then the correlations between 1 and 3 can be destroyed depending on what 2 is. So therefore 1 and 3 are not causally adjacent. They are causally related, but not causally adjacent. And then the earlier equality reduces to this, which symbolically you can write down. And the reason you want to write this down is to basically be able to specify the compositional compression omega set. So we said that lambda 1, 2, 3 was a subset of lambda 1, Cartesian producted with lambda 2, Cartesian producted with lambda 3. But here we find a form for what it looks like given these causally adjacent relations. So you can think of it as like, you can think of these Ks as these labels. So you can plot the L1 indices on one axis and like L2 on another and L3 on another, and you can try to see how these intersections work. And pictorially, then K would lie in this black space. And note that, so to get to this equation, you need some intuitions, and these kind of intuitions are based on how to, so we are used to thinking of theories with also omega sets that can be Cartesian producted, which I will mention again for quantum theory. For quantum theory, this holds. So you can look at this inequality, and actually we are interested in characterizing this, even though we know cases of this, but this is not the most general case. So here you can think of these as different wires are independent, so their indices are independent, something like that. Okay. Okay, so now I just want you to remember this slide. We will keep coming back to it, but what in the slide? This image, and this image corresponding to these lambda matrix relations and these omega set relations. And therefore, going forward in some framework, if we are able to write this framework in terms of the causaloid objects, if we can define the generalized measurement, generalized state, if it's written in an operational manner, then we can try to parse it and see if it obeys these conditions. And if it does, then we know that it falls in this hierarchy in this particular way. And even though we take the specific case, in principle, one could consider all kinds of causal relations between these three regions and find the subsequent notations. One more important comment I'll make at the expense of being pedantic is that here some of you should ask me now that, well, you know, you have this lambda matrix applied first and this one second. What if you had it the other way? So in principle, you can do this. You can apply it the other way, and then the form of this equation changes slightly. Nonetheless, the structure of this omega set stays the same. As you can see, it is symmetric in 1 and 3, and it doesn't capture the order of these lambda matrices, even though here you do because you're summing over things. Okay, good. So now we will apply the Causaloid framework to two things. So this is part 1 and part 2. So the part 1 would be to the DO tensors, which I'll mention again what they mean. And then the second part would be to these bipartite process matrices, which you saw in Fabio's talk sometime this week. So let's start with the DO tensors. So the DO tensors, I'm aware that maybe not everyone is familiar with them, and that's completely fine. But you can think of the DO tensors as this diagram here. It's this diagram where you have different ways to combine fragments. You can think of this as A, B, C as some operations, H as some operation, and then you join these fragments such that if you don't have any wires left open, it corresponds to some probability of some event. And now it looks awfully similar to what a quantum comb is, because this ABC looks like a quantum circuit, and this H looks like a quantum comb because it takes these channels and gives you probability back. But here you're not assuming a Hilbert space structure. Here you actually have a generalized probability theory underlying this. So therefore, the DO tensors are a class, a subset of generalized probability theories that follow certain rules. And one of the rules is called local tomography. And what that loosely means is that these wires A, B, and C are independent, meaning that irrespective of what is sent over B, if you wanted to do tomography of A, all you needed to do was tomography of these wires A, B, and C, and you didn't need any measurements on B, C together to characterize the tomography, to do the tomography of the operation. And once you have these assumptions in there, you can use them to show something, and which we will do now. So above we have the Causaloid framework equality we talked about. And now what we are going to do is we are trying to write down the probabilities associated with the DO tensor and massage the equation in a very explicit form. Now you can see that I've just opened these labels, and there are these white and black dots, which are part of the DO tensors. It is attributed to the word duo of the DO tensors because they are like tensors, but they have different types of wires, and there are rules of how they compose. And all of that is maybe outside the scope of this talk, but if someone wants to talk to me about DO tensors, I'll be happy to later. But one can now rewrite this here. The only thing happening from this step to this step is we've added these 3 circuits, and this circuit, this loop with these 2 triangles, this is a circuit which has probability 1. So you can just put them in there, and now you can compare this drawing to this drawing to identify the lambda matrices of the DO tensors in the Causaloid framework. And once you do that, you find that you can write down the lambda matrix. This lambda matrix is the compositional compression of 3 regions. And then you have the compositional compression matrices of 2 regions pairwise. And now we said that for lambda O2 sufficiency, you want to be able to write this in terms of these 2. So now in the DO tensors, that is asking if this can be written in terms of these. And it is possible precisely because of local tomography, that you can write these wires separately. And once you have that, you can actually show that any lambda O3 matrix can be written in terms of tomographic compression and these elements in the DO tensors, which correspond to elements of 2-region compositional compression only. And therefore, at the end of the day, what you've shown through this is that the DO tensors fall on the second rung of the hierarchy we defined with respect to meta compression, which is a reminder of which is here. Okay, so a whole class of GPTs we know of fall within the second rung. So now let's ask another question of what about indefinite causal structure, models of indefinite causal structure we know. So the most popular one, the one that has been most studied in the literature is the process matrices. So let's take a bipartite process matrix. We ask the same question. So on the top, you have the same thing from before, the Causaloid framework relation that is required to be satisfied if you want to show that something falls in the second rung of the hierarchy we defined earlier. And now let's go to a process matrix. So process matrix is, so here you have A and B. A and B correspond to some CPTP maps with some input and output Hilbert spaces. And a process matrix is a bilinear map on these CPTP channels that gives you a probability back. And so it's also defined using this Choi-Jamil-Koski isomorphism and writing the Choi states for them. Nonetheless, for us, what is pertinent is that we will associate. So for the Causaloid framework, we need to associate regions. And we'll do that. We'll assign A to be a region, B to be a region, and the process matrix W. I mean, I think I wrote P here, but most people use W. So let's stick to W. And then you can write down the omega sets and the lambda matrices. So here we are showing the omega sets for A, B, the process matrix W. And now you want to also be able to write down the omega set for the compositional compression of A and B. But without W, A and B cannot be compressed. They are just independent. So there is no compositional compression here, meaning that A and B are these regions 1 and 3 that are not causally adjacent. But on the other hand, when you compose the process matrix with A, you get a different process matrix back that can take one channel and give you a probability. So it becomes a comb in a way. And so this you can specify, you can do the same for BW when you compose B and W. But when you compose ABW, you get probability back. There are no indices anymore, and it's a single a set with a single element. And now if you carefully go through the lambda matrix calculation, you can actually see that these conditions above that we have written down are also satisfied by bipartite process matrices. And now, okay, so what have we learned? So let's try to see this schematically of this categorization of this landscape of logically possible theories done through an operational manner in the Causaloid framework. So we have two competing hierarchies. The first one I didn't mention because it's not new till now, but now it's pertinent to mention it. So it has to do with the tomographic compression. So I touched on it briefly when I said that for a qubit, you need 4 real numbers, and for a classical bit, you need 2 real numbers to specify the state without normalization. And actually, you can write this down in a very particular way by asking the number of real numbers you need to specify a state in some GPT, and the number of distinguishable states, perfectly distinguishable states. And then you get some parameter R, and the values of R change for different theory. So for classical theory, it's 1, but for quantum theory, it's 2. So one use, like in the reconstruction of quantum theory, people use this to be able to differentiate classical and quantum from a principled approach, as opposed to other ways. And now what we have shown is that, so this is one compression axis. The other one corresponds to this hierarchy we have introduced with respect to compositional compression. So we had this lambda OD sufficiency for various Ds. So here the parameter spaces are, and here it's D. And for D equals to 1, we didn't really care about this, as I said. For D equals to 2, we have shown that the duo tensors, which so the classical probability theory and So classical probability theory and quantum theory are special cases within the duo tensors. So when we show that the duo tensors fall in this rung by, we have also shown that classical probability theory and quantum theory also fall in this rung. And then we also, so this, the work with bipartite process matrices is ongoing work with Natalia Moller. And here we are showing that it also falls in this rung. So what does this really mean? What do we learn from this? How do we go from this point? And ideally, it would have been interesting to be able to differentiate indefinite causal structure phenomena in this hierarchy, but it seems like everything we know falls there, at least. And I mean, there are other things we need to check, of course. But this could mean that, well, maybe we don't really need to care about the rest of the space. So if you think of the Causaloid framework as a scaffolding which gives you a landscape of theories, and you need some principles to constrain it to be able to get some finite version of quantum gravity within it, then this could be one of those principles which says that, okay, let's restrict ourselves to lambda O2 sufficiency. But this is just, I'm just telling this as a direction in which we can go in, but this is not something we have concretely done yet.
So Nitica, means about 10 minutes for the main talk, and then we can take a couple of questions.
Great. Okay. No, so I just have, I think, maybe 2 slides more, which is just the outlook. So
Okay,
that's great.
fine. Yeah. So we'll have enough time.
Yeah. Good. So I was just talking about these directions. So one was that we can think of this as a restriction to this space and use this to study, use this as a principle to disregard the rest of the space. And the other thing one can do is actually try to construct a toy theory that falls in some lambda O3 sufficiency. And one way to do that, which is a project which we haven't finished yet, but it's trying to construct the trio tensors analogous to duo tensors, using the same mechanisms, but generalizing it. And I think this is my last slide. I should have had a thank you slide. I don't, but I am thankful. But this is the last slide to give you just a roadmap for what we're trying to deal with. Here we have quantum theory. When you operationalize it, you work more with quantum information. And then to go towards post-quantum theories, one space is GPTs, as I mentioned, and the other is indefinite causal structures. And really both of these go back to the Causaloid framework, within which we expect that an operational version of quantum gravity should be sitting as a point in this landscape. So that's where I'll end. Maybe I'll keep the slides up, and depending on what questions we have, and if not, then I'll stop the sharing as well. So thank you for having me, and please ask me any questions you have.
So the floor is open for questions. Means I can see there are more than 60 participants. So I hope there will be many questions. You can unmute yourself and ask questions. If you have any question, just unmute yourself and ask questions. Or alternatively, if your mic is not working or from some other reason, you can write in the chat box also.
Usually if someone's typing, it takes some time to be formulated. But I would encourage people to ask questions, even if you're shy or if you think the question is not well formulated, it's fine. This is the right forum for it, I think. And of course, like, feel free to write to me if you have questions as well.
Can I ask a question?
Yes, please.
Yes, thank you for your talk. What is the full form of CPT? Completely positive theory or what?
So CPTP maps that I was talking about?
Yes.
So completely positive trace preserving maps. So in quantum theory, you have unitaries, but a more general form are CPTP maps.
It means the density matrix should have positive eigenvalues, right?
It just means
This
that
is
it's a
what
map
you-
that can take a valid density matrix to a valid
Yeah.
density matrix, as opposed to a unitary which takes you from pure states to pure states and stuff like
Yeah,
that.
So diagonal element should be more than equal to 0.
Yeah. I mean, it's So
Are you going to consider nonlinear interactions also, or because here, if I understood correctly, you are considering only linear interactions?
so uh, so when you assume an operational framework, you have this requirement that you get probabilities back. And when you assume this, you need some linear structure because probabilities themselves have this linear structure embedded in them. So when people study these generalized probability theories, they are quite general, except that at the end you want a probability that's real, that's coming back, and these probabilities should add to 1. And that actually gives you this linearity requirement. So that's why we assume this. Yeah.
Okay, thank you.
Any other question?
Excuse me. Hello?
Please continue.
Yes, we can hear you.
Yeah. This is not a question, this is a request. Can you suggest few papers regarding this, like maybe in the chat, so that we can get like for beginners like us, it's really difficult.
Yeah,
So yeah,
but what kind of things you want to learn about, like this Causaloid framework or more
the
indefinite
GPT part, the
The
GPT
GPT,
part,
yeah.
GPT, and as well as the causality framework. Yeah, thank you.
Okay. So I think like I can do this right away, but is it possible that I send like an email to the organizers and they can somehow forward this information to students?
Yeah, sure, no problem.
Yes, that can be done.
Yeah, so I'll do this. I'll collate it into a document and I'll just send it to the organizers and hopefully they'll pass it along.
So, means in your structure, where you place the other theories, means which has a general structure like generalized local theories or generalized no signaling theories.
So if you're talking about no signaling like Bell correlations, is that what you mean? Or
Yes, means.
So you can study Bell correlations within GPTs because I mean you must have seen this very famous
Signaling
diagram.
is means that just you are adding that means faster than light communication is not allowed. So signaling is not allowed, and then there are general structure of theories which allows everything else. Means correlations is not limited, but signaling is not
Exactly. Yeah. So that falls within the purview of generalized probability theories already, because you know this diagram with if you see the Bell inequalities, but in this non-local game version as opposed to the CHSH version, then you show that there the bounds are 0.75 for classical, and then the Searleson bound is 0.85. And then for the logical one, you have these PR boxes. But these PR boxes are an example of generalized probability theories. So there, what you do is you, as you said, like you have this principle of no signaling, which you can impose. But you're working with subsystems, and these subsystems are general, and they can be written as GPTs. Yeah.
So is there any other question? So especially for students, means even if you are for some reasons you are not asking questions at the moment, if you want to drop a mail, you can also drop a mail to a speaker.
Yes, please. Like feel free to, and I think maybe my email should be available, but maybe I'll also write my email in the chat.
That makes sense. Means you can write your mail and then
instead of people trying to look for it. I'm giving my Gmail because it's something that's more permanent than university emails, and I just prefer it this way. So, and maybe
thanks
in the
for
next
talk. Thanks for addressing a student's query in the mail and everything.
Yeah.
And now we'd like to thank the speaker once again and for a beautiful talk. and
Thank
move
you.
to